Morning. As the last class we discussed about the correlation, cross correlation, auto correlation, and its properties. Okay, and some problems related to correlation and auto correlation, cross correlation. Okay, and already we have started the sampling theorem also, right? So how the sampling theorem describes. So again we will see. So sampling, what is meant by sampling is nothing but the process of converting a continuous time signal into discrete time signal. Process of converting continuous time signal. So a sample of continuous time signal is taken and it can be frozen for some time and can be divided into equal intervals of time. That is called sampling process. So that discrete time signal can be constructed from the continuous time signal. Okay, so a sample of continuous time signal can be taken, which can be frozen for some time and divided into equal intervals of the time. This is called sampling process, and the signal is called discrete time signal. So after sampling, the signal is defined at discrete instance of time, and the time interval between two subsequent sampling instances is called sampling interval. Okay. So the signal is defined at discrete instance of time, and the time interval between two subsequent sampling instance is called sampling interval. Here, one of the important factors is the signal sampling rate must be kept sufficiently high. This is very important factor. That is, signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. First of all, the continuous time signal mm, can be converted into samples and it can be reconstructed into the original signal. Okay, so here we have to notice the important factor as the signal sampling rate must be kept sufficiently high. Okay, it is represented diagrammatically as, see, it is represented diagrammatically as, so f of s, so x of t is the input for the system. Okay, having the frequency sampling frequency 1 by t. Okay, its output is x of n is equal to x of nt. So it can be converted into the continuous time signal x of t can be converted into discrete time signal x of n equal to x of nt. These are the samples. So x of nt is a sampled sequence of x of t. Or we can also represent this as x of t is multiplied with the train of impulses. These are train of impulses. Impulse function is delta of t. Delta t of t is nothing but the train of impulses. By multiplying these two, we will get the sample sequence x of nt like this. So x of t is the continuous time signal. So the delta t of t is nothing but the train of impulses. These two are multiplied so that we will get the sample sequence of x of t, that is x of nt. So x of nt versus nt graph is like this. So the signal, this is called discrete time signal. It can be divided into equal intervals of the time, right? So these diagrams are related to the sampling operation, where capital T is nothing but time interval between successive samples. Successive samples and the sampling frequency is given by Fs equal to 1 by T Hz. Okay, another way of representing the discrete time signal is excess of T, sample version of sample sequence excess of T is equal to x of T multiplied with the train of impulses delta T of T. That is considered as equation number 1, where delta T of T is equal to sigma, these are train of impulses sigma n equal minus infinity delta of t minus nt. These train of impulses are represented like this: sigma n equal minus infinity to infinity delta of t minus nt. That is equation number 2. That is the function x of t is the product of x of t and the train of impulses. Therefore, x of t is equal to sigma n equal minus infinity to infinity x of nt into delta of t minus nt. Okay, delta of t minus nt, that is considered as equation number 3, right? For this equation number 3, applying Fourier transform to equation number 3, we get Fourier transform of x of t is equal to Fourier transform sigma n equal to minus infinity to infinity x of nt into delta of t minus nt, right? So this will become sigma n equal to minus infinity infinity x of nt into Fourier transform of delta of t minus nt. Okay, that it we consider as equation number 4. But we have Fourier transform of delta of t minus nt is equal to integral minus infinity infinity delta of t minus nt into e power minus j omega t dt. This is Fourier transform of x of say x of t. So this is x of t, right? Delta of t minus nt into e power minus j omega t dt, which is equal to e power minus j omega nt. Okay, that is equation number 5. Therefore, x of e power j omega is equal to Fourier transform of x of t is equal to sigma n equal minus infinity infinity x of nt into e power minus j omega nt. That is equation number 6. But we know that delta t of t, train of impulses, is equal to sigma n equal to minus infinity infinity delta of t minus nt, which is equal to 1 by t into sigma m is minus infinity infinity e power jm omega naught t, which is equation number 7, where omega naught is 2 pi by t. So therefore, xs of t is equal to x of t multiplied by delta t of t, that is 1 by t into sigma m is minus infinity infinity e power jm omega naught t. Omega naught is replaced by 2 pi by t. Okay, or we can write this as 1 by t into sigma m equal to minus infinity infinity x of t into e power jm omega naught t, which is equation number 8. Okay, therefore Fourier transform of xs of t is equal to 1 by t into sigma m is minus infinity infinity Fourier transform of x of t into e power jm omega naught t. That is equation number 9. If Fourier transform of x of t is x of j omega, then Fourier transform of x of t into e power jm into omega naught t, which is equal to x of j omega minus m omega naught. By substituting equation 10 in equation number 9, we get Fourier transform of x of t is equal to 1 by t into sigma m is minus infinity infinity x of j omega minus m omega naught t. Okay, so it is equal to 1 by t into sigma m is minus infinity infinity x of j omega minus m is 2 pi by t into omega naught is 2 pi by t into m. That is equation number 12. Thus, the Fourier transform of the sample signal is given by an infinite sum of shifted replicas of the Fourier transform of the original signal. So that is this equation can be represented as Fourier transform of the sample signal, that is f of x of t, is given by an infinite sum. This is varying from minus infinity infinity. That's why we can say that it is infinite sum of shifted replicas. So these are the shifted replicas of the Fourier transform of the original signal. Okay. So now consider the signal x of t is band limited to fm. That is the highest frequency component of x of t is fm. Then x of j omega is equal to 0 for mod omega is greater than omega m, where omega m is 2 pi by t or 2 by fm. That is equation number 13. So it is as shown as so it is band limited to fm, which can be represented like this: x of j omega is varying from uh, minus omega m to plus omega m frequency spectrum of CT signal. This is the frequency spectrum of CT signal. Then excess of j omega is frequency spectrum of x of nt with pi by t is equal to omega m, which can be represented like this: pi by t is equal to omega m. Then in C diagram, frequency spectrum of x of nt with pi by t is greater than omega, so which can be represented like this. And in last case, frequency spectrum of x of nt with the pi by t is less than omega n, so it can be represented like this. So here there is some overlap will occur. So this is the overlapping of these two samples. Okay, this is called aliasing. Here aliasing occurs in the above diagram. We can prevent this aliasing error if the highest frequency component omega m in the signal x of t is less than or equal to pi by t. So that is omega m is less than or equal to pi by t. Okay. or pi by t is greater than or equal to omega m. Okay, the highest frequency component omega m and the signal x of t is less than or equal to pi by t. Okay, so if fs equal to 1 by t, then pi into fs is greater than or equal to pi into fs is 1 by t is fs, so pi into fs is greater than or equal to omega m. Then pi fs is 2 pi into fm, so pi gets cancelled, so fs is greater than or equal to 2 fm. This is equation number 14. This is very important. Sampling frequency is greater than or equal to 2 times of maximum frequency, right? 2 times of fm. So now we can define the sampling theorem as a band limited signal x of t with x of j omega is equal to 0 for mod omega greater than omega m is uniquely determined from its samples x of mt if the sampling frequency fs is greater than or equal to 2 into fm, that is double the sampling frequency must be at least twice the highest frequency present in the signal. So sampling frequency must be at least twice the highest frequency present in the signal. So that is the sampling theorem, sampling theorem condition. Sampling frequency is greater than or equal to 2 into fm. Sampling frequency is 2 times greater than or equal to 2 times the highest frequency present in the signal. Okay, this is the sampling theorem. So it is defined as a band limited signal x of t with x of j omega is equal to 0 for mod omega is greater than omega m is uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2fm, that is sampling frequency must be at least twice the highest frequency present in the signal. Okay, that is the definition of the sampling theorem. Now coming to the Nyquist rate. What is meant by Nyquist rate? Nyquist rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. Okay, okay. The signal, which is the minimum rate, sampling rate is Nyquist rate is okay. The minimum rate, Nyquist rate is the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. It is always equal to 2fm, where fm is maximum frequency component present in the signal. This 2fm is called Nyquist rate. So it is the minimum rate at which signal can be sampled and reconstructed from its samples is called Nyquist rate. It is 2fm. Okay. If a signal samples at greater than Nyquist rate is said to be oversampled. A signal sampled at less than Nyquist rate is called undersampled, and so it is greater than the Nyquist rate, it is called oversampled. It is less than the Nyquist rate, it is the undersampled. Next, coming to the anti-aliasing filter. So this is about the Nyquist rate. It is the minimum rate at which the signal can be sampled and reconstructed from its samples. Reconstructed from its samples is called Nyquist rate. It is mathematically represented as 2fm. Next, we are going to discuss about the anti-aliasing filter. Anti-aliasing filter. Anti-aliasing filter. A filter that is used to reject high frequency signals before it is sampled to reduce the aliasing is called an anti-aliasing filter. So a filter is a filter that is used to reject high frequency signals before it is sampled. Before it is sampled to reduce the aliasing is called an anti-aliasing filter. Diagrammatically, it is represented like this. So this is anti-aliasing filter. So its input is x of t before the sampling, before the before the sampling is the sampler, and output is x of n. So it rejects high frequency signals before it is sampled to reduce the aliasing. It is called anti-aliasing filter. Now we are going to discuss about the signal reconstruction. So far, our signal can be converted into sampled version of the signal. So how to reconstruct this signal? So from this sampled version, it can be reconstructed. Okay, from the sampled version, it can be reconstructed so that we will get the original signal. So signal reconstruction, as we already discussed earlier, that the bandwidth signal XRP can be reconstructed from its samples if the sampling rate is above Nyquist rate. Okay, if the sampling rate is above Nyquist rate. Nyquist rate is a 2 FM. Sampling rate is a fs is greater than 2 FM. Okay, let the sample signal excess of t with the sampling period 3 seconds is excess of t is equal to sigma n equal to minus infinity to infinity x of nt into delta of t minus nt. Let it be considered as equation number 1. Now taking the Fourier transform for this one. So excess of t, Fourier transform of excess of t is x into e power j omega is equal to 1 by t into sigma m is minus infinity to infinity x of j omega minus 2 pi n by t. That is equation number 2. The frequency spectrum x into x of e power j omega consists of an infinite sum of shifted replicas of the frequency spectrum of the original signal. Already we discussed it. To get the original spectrum of the signal, excess of t is to be passed through a reconstruction filter. It has to be passed through a low pass filter with an impulse response h of t. Right? So excess of t and impulse response h of t, so that we will get the original signal. The original signal can be obtained by convolving the sample signal excess of t and the impulse response h of t of the filter, that is x of t equal to excess of the convolved with h of t, or we can write this as excess of t sigma n is minus infinity infinity x of nt into delta of t minus nt convolved with h of t. Okay, or we can write this as integral minus infinity infinity sigma n is minus infinity infinity x of nt delta of t minus nt and tau uh, nt into h of t minus tau t tau. Delta of t minus nt is equal to 1 for delta equal to nt and is 0 for delta is not equal to nt. Okay, we can write this as sigma n equal to minus infinity to infinity x of nt into integral interchanging the order of summation and integration. So sigma n equal to minus infinity infinity x of n tau into integral nt into integral minus infinity infinity delta of tau minus nt into h of t minus tau d tau. Okay, so that x of t will become x of t equal sigma n equal minus infinity infinity x of nt into h of t minus n tau. That is equation number 3. So the frequency response of the low pass filter can be expressed by h of j omega is equal to t for mod omega is less than or equal to omega s by 2 and is 0 for mod omega is greater than omega s by 2. That is equation number 4. So the frequency response of low pass filter is as shown like this. So h of j omega versus omega. So its amplitude is t. Okay, it is varying from minus omega s by 2 to omega s by 2. Okay, its value is t for mod omega is less than or equal to omega s by 2 and is 0 for mod omega is greater than omega s by 2. This is the frequency response of low pass filter. So the impulse response of the low pass filter is h of t is equal to 1 by 2 pi into integral minus omega s by 2 to plus omega s by 2 h of j omega into e power j omega t t omega. So it will become h of j omega is t, so that t by 2 pi into integral minus omega s by 2 to plus omega s by 2 into e power j omega t t omega, or it is nothing but t by pi t into sin omega s by 2 omega s into t by 2. or it will become t by pi t into sin pi t by t, or t by pi into sin pi t by t by t, which is equation number 5, or h of t minus nt is equal to t by pi into sin pi by t into t minus nt by t minus nt. That is equation number 6. On substituting equation number 6 in equation number 3, we get x of t equal to sigma n is minus infinity infinity x of nt into sinc pi by t into t pi by t into t minus nt. That is equation number 7. Here, sync function spreads over entire time axis. To reconstruct the signal at time t equal to t naught, we must know all the sample values, including those for nt is greater than t naught. So it represents a non-causal system. Hence, the type of reconstruction is not suitable for real-time applications. So, reconstruction type of reconstruction is not suitable for real-time application. Okay, this is about the reconstruction of the signal. Therefore, we need a different approach to convert digital signal to analog signal. Digital signal to analog signal. Here, digital to analog converter produces output voltage that is proportional to the value of the binary word. Okay. Okay. So the digital to analog converter produces output voltage that is proportional to the value of the binary word. The output of DAC. So here DAC is applied to an interpolator in the diagram. Digital to analog converter. The output of DAC is applied to an interpolator which converts the output samples of DAC into analog signal, right? So there are several interpolators. Okay, digital signal. So this is the interpolator. See, DAC, digital analog converter output is connected to interpolator. What is the role of interpolator, which converts output samples of DAC to analog signals? These analog signals are passed through a low pass smoothing filter, so that smoothing analog output signal is obtained. Okay, right? So several interpolators are there. Here we are using one type of interpolator that converts the output samples of DAC to analog signal. Okay, these can be smoothened by low pass smoothing filter. Okay, so next we are going about the zero order code. What is meant by zero order code? Okay, zero order code. One of the most widely used interpolator is zero order. It is one of the interpolator, zero order hold interpolator. In this technique, a given sample is held for an interval until the next sample is received. Okay, given sample is held for an interval until the next sample is received. Mathematically, xc of t, xc cap log of t is equal to x of n for nt is less than or equal to n is less than or equal to n plus 1 into t, where n is 0 to n. In particular, xc of t analog is equal to x of 0 for 0 is less than t is less than t. X of t, if it is t for t is less than 2t. X of 2t, x of 2t for 2t is less than 10 is 2. So it is 2t. So for 2t is less than or equal to t is less than t. So this is the signal zero order hold. By applying if this signal is passed to zero order hold, it will become analog signal XA of t. And finally, we'll obtain the signal like this. Okay. The impulse response of a zero order hold is given by h of t is equal to 1 or 0 is less than or equal to t is less than or equal to t and is equal to 0, otherwise h of t equal to 1. Next we will see the transfer function of a zero order hold. Transfer function of a zero order hold. Now we will see the output of zero order hold. So if you take the output of zero order hold is expressed in terms of h of t, that is the output xA cap t is the convolution of x of nt and h of t. H of t is the impulse response. So by convolving x of nt with h of t, so that we will get xA of analog signal xA of t. So xA of t is equal to sigma n is minus infinity infinity x of nt into h of t minus nt. H of t in equation 10 can be expressed as h of t equal to u of t minus u of t minus nt. That is equation number 12. In general, h of t minus nt is u of t minus nt minus u of t minus n plus 1 into t, right? So substituting equation number 13 in equation number 11, we get xa of t is equal to sigma n is minus infinity infinity x of nt to h of t minus nt is u of t minus nt minus u of t minus n plus 1 into t, right? So taking Laplace transform on both sides, we get Laplace transform of xa cap t is equal to sigma n is minus infinity infinity x of nt into Laplace transform of this entire expression u of t minus nt minus u of t minus n plus 1 into t. Or we can write this as sigma n equal minus infinity infinity x of nt into Laplace transform of u of t minus nt is e power minus s nt by s, and Laplace transform of u of t minus n plus 1 into t is e power minus s into n plus 1 into t by s. Okay, so taking 1 minus 1 minus e power minus st as common, 1 minus e power minus st by s as common into sigma n equal 0 to infinity x of nt into e power minus s nt. Okay, so that it will become 1 minus e power minus s minus cs e power minus st by s into x star of s. So xa of s by x star of s equal to 1 minus e power minus st by s. So the output of zero order hold consists of higher order harmonics. The output of zero order hold consists of higher order harmonics. To remove these harmonics, the output of zero order hold is applied to a low pass filter as shown in figure 1. The filter is low pass filter. So this is the figure 1. Okay. So the output is applied to the zero order hold is applied to a low pass filter as shown in figure 1. This filter is often called a smoothing filter because it tends to smooth the corners of the step approximations. Okay. Now we'll solve the problem. Find the convolution of two finite sequences given below. Also verify the result by using treasure, treasurer method. This is called treasurer method. Okay, x of n is given as 2. For 0 is less than or equal to n is less than 3. It is 0 otherwise. Okay, and y of n is given as a set of 1, 2, 3, 2, 1. Here 3 arrow mark is given at 3, that is y of 0. Left side y of minus 1 is 2, y of minus 2 is 1, and y of 1 is 2, right side, and y of 2 is 1. Given that x of n, what is x of n? X of n is given as 2 for 0 is less than or equal to n is less than 3. From 0 to 3, its value is 2. Okay. 0 is less than or equal to n is less than 3. Okay. Or it is 0 otherwise. Okay. So x of minus 1 value is 0. X of 0 is 2. X of 1 is 2. X of 2 is 2. Right. So therefore x of n is equal to 2, 2, 2. Arrow mark is given at first one, that is x of 0. Similarly, y of n equal to y of minus 2 value is 1, y of minus 1 value is 2, y of 0 value is 3, and y of 1 value is 2. Similarly, y of 2 value is 1. So by replacing independent variable n by dummy variable k in x of n and y of n, it will become x of k and y of k. So x of k will become 2, 2, 2. Y of k will become 1, 2, 3, 2, 1. H of n is nothing but x of n converted with y of n. Or we can write this as sigma k equal to minus infinity to infinity x of k into y of n minus k. Okay. So our h of n equals sigma k equal to 0 to 2. Okay, x of k into y of n minus k, that is equation number 1. So expand equation number 1, we get if k is 0, then x of 0 into y of n, x of 1 into y of n minus 1, x of 2 into y of n minus 2. Okay, so le of h of n, left hand side of h of n equal to le, left hand left hand of left hand of x of n plus left hand of y of n. Okay, so what is left hand of x of n? Left hand of x of n is 0. What is left hand of y of n? That is minus 2, y of minus 2. So left hand of x of n is x of 0. Okay, 0 plus minus 2 minus 2. So right hand of h of n is right hand of x of n plus right hand of y of n. So right hand of x of n is x of 0, x of 2, and this is also 2. 2 plus 2, 4. Okay. So h of n get to be computed from minus 2 to 4 only for n equal to minus 2. So therefore h of minus 2 to 4, h of minus 2 can be calculated as 2. In the same manner, h of minus 1 is calculated as 6, h of 0 is calculated as 12, h of 1 is calculated as 14, h of 2 is 12, h of 3 is 6, and h of 4 is 2. So finally, h of n values are 2, 6, 12, 14, 12, 6, 2, and h of 0 value is 12. Okay, like this. We can do the convolution for the both x of n and y of n, right? With this, it is completed. So sampling theorem is very, very important, and reconstruction of the signal is also very important from the sampling theorem. In convolution, autocorrelation, cross correlation, autocorrelation, relation between convolution and correlation, all these things are very, very important in this unit. Okay. This class, tomorrow we'll go for the next topic. Okay, thank you.